Why are Linux kernel bugs so hard to reproduce? Imagine trying to catch a shadow that changes shape every time you look for it. That's what debugging Linux kernel bugs can feel like. The Linux kernel is the core of many operating systems, managing hardware and software interactions. Because of its complexity, bugs in the kernel are often tricky to find and fix. One big reason is that the kernel runs many tasks at once. It supports multitasking, which means multiple threads or processes work together. These threads can switch places randomly, depending on how the system schedules them. If a bug depends on a specific order of thread execution, it might only show up sometimes. That makes it hard to recreate the exact conditions needed to see the bug again. Inputs also play a big role. The kernel handles data from hardware like disks, network cards, and keyboards. Small changes in this data can cause different behaviors. For example, a tiny difference in network traffic might trigger a crash one time but not the next. Because inputs are so varied and unpredictable, reproducing bugs that depend on specific inputs becomes a real challenge. Memory management adds another layer of difficulty. The kernel dynamically allocates memory for different tasks. This means the location of data in memory can change each time the system runs. Bugs related to memory, like corruptions or use-after-free errors, might only appear under certain memory layouts. If the memory layout changes, the bug might not show up again, even if the same code runs. Different versions of the Linux kernel also matter. Developers fix bugs in newer versions, but sometimes they introduce new ones. A bug in one version might be fixed or behave differently in another. So, reproducing a bug requires matching the exact version and branch of the kernel used when the bug was first seen. Debugging tools like sanitizers can influence how bugs appear. These tools check for errors but can also mask or trigger bugs differently depending on how they are configured. Running the kernel with different sanitizers or debug options can change the behavior, making consistent reproduction harder. Compiler optimizations are another factor. When code is compiled, the compiler can inline functions or reorder instructions to make programs run faster. These changes can alter how bugs manifest at runtime. A bug that appears in one build might not show up in another because of these optimizations. All these factors highlight how the Linux kernel's design makes bug reproduction a puzzle. Unlike user applications, the kernel works directly with hardware, manages multiple tasks simultaneously, and relies on timing. This makes bugs highly dependent on tiny timing differences, specific inputs, and memory states. To troubleshoot these bugs, developers use special techniques. They control inputs carefully, add delays to expose thread interleavings, run tests repeatedly, and match the exact kernel version. They also use consistent debugging environments to avoid masking bugs. These steps help them catch issues that are hard to reproduce naturally. In the end, the difficulty in reproducing Linux kernel bugs shows how complex and powerful this core system component is. Its ability to handle diverse hardware and multitask efficiently comes with the challenge of unpredictable bugs. That's why fixing kernel bugs often takes patience, precision, and a lot of testing.